All right, so hi everyone. We're continuing our recitations and considering new ways of integration. So we'll get started. Now, going forward for pretty much the rest of the summer, we're just going to be looking at different kinds of integrals. And there are a lot of different integrals that we've seen so far. So let's just do a quick recap of some of the integrals that we've seen. So the obvious one is just the regular old single line integral in from Calc 1 and Calc 2, but that's just the integral over r from a to b of fx dx. And we've got double integrals that we do in R2, and usually there are two ways of calculating them, either using Cartesian coordinates or polar coordinates, excuse me, which are discussed in sections 15.1 through 15.3 if you want to brush up on those. And we've got triple integrals, which are volume integrals. Often that's what they're called, as volume integrals. And again, you can calculate those using either Cartesian, aka rectangular, cylindrical, or spherical coordinates, and that's in sections 15.6 through 15.8 if you want a reminder on those. Now we're in chapter 16, and in section 16.2 we introduced two new kinds of integrals, namely line integrals. And there are two flavors of line integrals. There are either line integrals of scalar functions and line integrals of vector fields. So a lot of different kinds of integrals we've looked at so far, and the thing that I want to point out to everybody is there will be more. We will be looking at more integrals over the remainder of this semester. So so keep your heads up. Okay, so here are some commonalities between these things. So because there are so many integrals, it can seem like there are a lot of formulas to remember, but there are some common threads and some parallels to draw between them that might make them a little bit easier. One thing is, if you look back at all of these integrals, for single, double, and triple integrals, okay, those usually represent some kind of a mass or volume or something, or area or something like that. Those are all scalars. And the same thing is true for line integrals. Line integrals of scalar functions, those are also going to be scalars. Again, you can think of those as the density of a wire, or over some curtain, or an area of some curtain or fence, or whatever you want, really. Line integrals of vector fields, now these are a little more nebulous and a little less geometrically intuitive, but they're work. Literally, they are they represent work in physics. So, and work is a scalar. Work is also a scalar quantity, and you can see that because there's a dot product here, right? You're taking a dot product of a vector field with this mysterious vector differential dr, and a dot product gives you a scalar. So all of these things are going to be scalars. Now, strictly speaking, this isn't 100% true, because we saw one example in section 13 of an integration that gives a vector instead of a scalar, but the geometric meaning of what exactly that thing is wasn't as clear. We really only used that to anti-differentiate velocity curves and things like that, but that's really all of that was, and it was more of a computational tool than anything actually geometric. And besides, it's just a repeat of single integrals on the real line, just done in 3 different coordinates. So it's really not that interesting in some ways. So we're not going to really pay attention to that one as much. Most of the time, with this one exception, most of the time, all of the integrals that we're looking at here are going to be scalars. Now, there's a very important principle behind all of these things, and that is the principle of syntax. What do I mean by syntax? Well, all these integrals should obey the same operation rules we've been studying. So, for example, this funny, I think it's French, but it might be Germanic. This long S thing, the integration symbol, in other words, that should be a sum. That is a sum of a thing. So because that's a sum, that should fall into our syntax. So if little f is a scalar function, then use a scalar differential, such as ds, which is length. So that's the sum of the scalar times length. Scalar times a scalar. Sum of a scalar times a scalar. And that's going to be a scalar. So that's okay. On the other hand, you could have that big F, big bold F, that could be a vector field. And if it's a vector field, we're going to use a vector differential. And a vector differential example of that could be dr, which is r prime t dt, aka that's a very small change in displacement. And we use a dot product of that with our with our scalar, with our vector differential and our vector field. So it's a dot product of the vector field with this vector differential. That's going to be a scalar too, but that obeys the same rule that we saw before. So in particular, you can't take a dot product of ds. ds is a scalar. You can't dot ds with big F. That doesn't make any sense. You can't take a dot product of a scalar and a vector. That doesn't work. So syntax is very important. If you make sure that you're obeying the rules of syntax, then pretty much everything that you're gonna get out of this is gonna work out. Now, by the way, I want to make a small note about some of these differentials, because there are a couple different differentials we've seen at this point. Now, remembering which one to use can be a little bit tricky, but the important thing is to ask yourself, okay, this differential, dt, dx, ds, dr, whatever, they represent a small change in something, right? A differential usually represents a small change in some quantity. What is that quantity, and what is that quantity over time? So for example, ds is usually used to represent a small change in length, right? S is arc length, so ds is a tiny change in length. What's length over time? Well, length over time is speed. Speed, which is the magnitude of r prime. So ds dt is magnitude r prime, or a little, so this is a, mathematicians refer to this as abusing notation, but basically ds is magnitude r prime t dt. On the other hand, dr, you can think of as a small change in displacement. And when I say displacement, what I mean is a change in length, but in a particular direction. And what's displacement over time? Well, displacement over time, that's velocity, right? So velocity, your displacement over time, is given by velocity. So the so dr dt is r prime, or dr is r prime t dt. That's a vector differential, though. So below, these are some examples, some of the many examples of nonsensical integrals that we have seen before in this class and when we teach this in person. So for example, you can't take little f of r of t times r prime, because that would be a scalar times a vector, which is technically allowed, but that would give you a vector, right? That's scalar multiplication, and that gives a vector. You want that to be a scalar. On the other hand, you can take little f of r of t dot r prime t dt. Now that doesn't make sense either, because you're then dotting a scalar and a vector. That's not going to work. Or you can take the vector field f of r of t dotted with the magnitude of r prime. You can't do that either, because the magnitude of r prime is a scalar, and you can't dot a vector and a scalar. Now, for those of you who are reading along with this and seeing what the point here is, this might seem obvious to some people, like, oh, well, of course you can't dot a vector and a scalar. Of course you can't do this. Of course you would want your length to be a scalar quantity and not a vector quantity. But we've seen these before. We've seen these kinds of examples, and we don't want you to make these. So these are just some examples of what we mean when we're talking about nonsense. So don't do this. Here's another good strategy. So those are the principles that I wanted to point out. The principles, just to recap, are, generally you want to be scalars and not vectors, and you want to obey syntax. Those are the important things. And if you're having trouble remembering what the differentials are, then just think about, okay, if this represents a small change in blank, what is blank over time? And that should help you remember what some of these differentials are. But that only applies for single integrals. We'll get to double integrals and more advanced double integrals later on. Now, a very good strategy is to write down the formula you think you might need. I did this a little bit when I was doing the, when I was working on the lectures. A very good strategy is just write down the formula that you think you need. Because if you just start there, if you can literally visually see all of the symbols and what you think you're going to need in the problem, then that will help you immensely. And I'm serious about this. There have been times when I've been in my office and I've had students working with me, and they'll say, "Oh my gosh, I don't know how to do this problem. What are we doing?" And I say, "Okay, just write down the formula you think you need." And as soon as they write it down, they'll say, "Oh, now it makes so much sense." So this is a very good strategy. Now, a quick note, most of the problems that I'm about to do for the recitation, I'm only going to be setting them up, mostly for brevity, but also you should become comfortable and familiar with doing some problems on your own. And I don't want to give away the entire problem in this recitation, because that kind of defeats the purposes as far as I'm concerned. Let's get started. Okay, so let's start off with this guy. So you've got the integral of x e to the y ds, and it's integrated over c, which is the line segment from 2, 0 to 5, 4. So let's see if we can get a sense of what this thing looks like. We've got, it's also a very good idea to try drawing a picture to get a sense of what this thing looks like. So you've got 1, 2, 3, 4, 5. It's from 2, 0 to 1, 2, 3, 4 to 5, 4, which is going to be up here or so. It's not exactly to scale, but that's okay. So here's our curve. It's this line segment. So how do you parameterize that? One of the, so that's what our figure looks like. So now how do you solve this thing? Well, in this case, we know that we're dealing with a vector, not a vector. We're dealing with a scalar function, x e to the y. So because we have a scalar function, and we know that ds, we said is change in length, or in other words, that's speed times a change in time. So we're going to use the formula integral over c of fxy ds. That's the integral from a to b of f of r of t times magnitude r prime of t dt, and that's a t over there. So what do we need? Well, we need an r of t, and more specifically, we need an r prime of t, and we need f of r of t. And we're also going to need to know what a and b. So, i.e., what we really need is we need to parameterize our curve. We need to parameterize our curve. So in this case, this is a line segment. It's a line segment from the position vector to 0 to the position vector 5, 4. And there's a standard way of parameterizing that. The standard way of parameterizing it is saying that r of t is equal to 2, 0 plus t times 5, 4 minus 2, 0. Or in other words, 2, 0 plus t times 3, 4. And if you want to write it as a single vector, that's fine too. 2 plus 3t, comma, 4t. All right, well, that tells us what r prime of t is. And we can then find its magnitude. What's the magnitude of the derivative? The derivative of that thing is just the vector 3, 4. And the magnitude of that derivative is root 9 plus 16, or in other words, 5. So that gives us that the integral that we want, the integral over c of x e to the y ds, what does that come out to? That's the integral from, important other point here, by the way. This standard parameterization works for t between 0 and 1. So in other words, that tells us that a is 0 and b is 1. Forgot to point that out. So this is the integral from 0 to 1 of x. We know that x is 2 plus 3t times e to the 4t times r prime of t, which is 5 dt. Or in other words, the integral from 0 to 1 of 10 e to the 4t plus 15 t e to the 4t dt. Now, this last integral, that's not terrible, although you would have to do some of it by parts. And I'm not going to do that. I'm not going to go through the entire antidifferentiation and integration step here. You should work this out on your own, but I'll tell you what the final answer is. The final answer here is going to come out to, I'm going to write it on the next line down, 85 over 16 e to the 4th minus 25 over 16. That's what the final answer is. That's what that thing works out to. Even though I'm not going to go through the whole thing, I will just point out that you would need to do this integral by parts. And if you're not sure how to do that, then I'd either spend some time reviewing that or ask for help on that in the guided study group, because that is an integration technique we expect you to know how to do. Okay. So one thing, by the way, that I should mention is, this is going backwards a little bit, looking at, writing out these formulas. So there are really 3 formulas that, these, 3 important formulas for integration that we've looked at so far, for chapter 16. One of them, 2 of them are just the bare bones, brute force, scalar and vector field line integrals that we had before, f of r of t r prime t, or big F of r of t dot r prime t. That second one, by the way, is equivalent to the integral of p xy dx plus q xy dy, and that's p of r of t x prime of t plus q of r of t y prime of t. That's literally the same thing, right? These two are literally the same thing if we consider, for example, r of t to be, x of t and y of t. And also that dr is dx comma dy. So these things are literally the same exact thing. So, so don't freak out if you see dx dy. That's just a vector field integral in disguise. Now about this next, or final formula here, this is the fundamental theorem of line integrals. The line integral of this vector field is the antigradient of r of b minus the antigradient of r of a, in other words, at the endpoints. But that's only true if your vector field does in fact have an antigradient. In other words, it's only true if big F is equal to the gradient of some little function f. This doesn't even make sense if that's not the case. So don't try to do this if you don't have an antigradient. Don't try to do this if your vector field is not, in other words, conservative. This doesn't even make sense. And by the way, this is another area, this is another way in which writing out a formula can be helpful. You can write out the formula, the integral of big F of dr is little f of r of b minus little f of r of a, but then you have to ask yourself, okay, what's little f? What is this little f function? It might not exist. And if it doesn't exist, you can't use that formula. So there are a lot of good reasons for writing out formulas, because it lets you see everything that you would need and what you have at your disposal, and sometimes they won't work. So it's a very good strategy to do that. All right, let's do this other example. Here we have the here we have another one of these. It's a vector field integral in disguise. In this case, this is pxy equals x squared, and qxy equals y squared. So really we're working with the vector field fxy is x squared I plus y squared j. That's a legitimate vector field. Now C is the arc of the circle, x squared plus y squared equals 4 from 2 to 0 to 0, 2, followed by the line segment from 0, 2 to 4, 3. So again, let's draw it out, see what this thing looks like. So, 1, 2, 3, 4, 1, 2, 3, 4. And what do we find? We find that in the first place, it's the arc of the circle, x squared plus y squared is 4 from 2, 0 to 0, 2. That's this piece right here. Followed by the line segment from 0, 2 to 4, 3, which is up here. So it's a two-piece curve, which means we would need to do this integral in two different pieces. Let's call this first one. Actually, I'm going to do this in two different colors to make it even more clear what's going on. Like one blue and one pink. So let's call this blue curve C1. Let's call this pink curve C2. Okay, so with all that in mind, now that we're doing this, let's see what we get. We have to do C1 first, or C2. Actually, it doesn't matter which one we do first, but we have to parameterize them either way, because what we need, this is the integral of f dot dr, where f is just been given up there. Integral from a to b of f of r of t dotted with r prime of t dt. That's the formula that we're going to need. So for C1, what does that give us? For C1, we can use our trigonometric parameterization, which would be x is equal to, in this case, 2 cosine t, because the radius is 2. Y is 2 sine t. Now, by the way, before I forget, t is going from 0 to pi over 2. Now, by the way, can you swap these? Can you say that instead we're going to say x is 2 sine t, y is 2 cosine t? In this case, no. In this case, no, you can't do that. And the reason you can't do that is because if you swapped them, if you swapped x is 2 sine and y is 2 cosine, then this curve would be going in the opposite direction, right? You would start up here. If it's x is 2 sine, well, then x starts at 0 and y is 2 cosine, y starts at 2. So you're going in the opposite direction in that case. You're reversing the orientation. But in this case, we're explicitly told it's going from 2, 0 to 0, 2. So you really have to keep it in this parameterization to ensure that you're going counterclockwise. If you're not going counterclockwise, you're going to get a different answer in this case. So it's important here to make sure that you've got x is 2 cosine, y is 2 sine. Okay, so now that means that I'm going to call it r1 prime of t is negative 2 sine t, 2 cosine t, and f of r1 of t. F of r1 of t is 4 cosine squared t I plus 4 sine squared t j. So the integral over C1, this first, the blue curve, of f dot dr, this is the integral from 0 to pi over 2 of, because I'm typing my office mate, the integral from 0 to 2 to 0 to pi over 2 of the dot product 4 cosine squared t I plus 4 sine squared t j dotted with negative 2 sine t, I'm going to run out of space, I plus 2 cosine t j dt. And all of that is going to come out to the integral from 0 to pi over 2 of negative 8 cosine squared t sine t I, not I, excuse me, it's a dot product, it's a scalar, plus 8 sine squared t cosine t dt. And I'll let you know what this is. This comes out to 8/3 cosine cubed t plus 8/3 sine cubed t not dt. Why did I say dt? I didn't mean that. Evaluated from 0 to pi over 2, which would in this case just be negative. Actually, excuse me. Which in this case would be 8/3 minus 8/3, which is 0. But now let's look at the at C2. Again, since again we can say that R of t is going from 2 not 2 0 0 2 plus t times 4 3, which in this case is 4t 2 plus 3t. So in this case, that means that R prime of t is just 4. Wait, rats. No. I'm making a terrible mistake. Don't do what I just did, because what I just did is I forgot to subtract these. 4/3 minus 0 2. Excuse me. Terrible mistake on my part. So what this should actually be is 4t comma. Let me write that a little bit lower. 4t comma 2 plus t. 4t going from 0 to 1. So R prime of t is equal to 4 comma 1. Am I doing this right? Yeah, I think I'm doing this right. So, and it's always okay to check your parameterization, to double check to make sure everything is working out the way you want it to. And in this case, I'm reasonably sure that it is. So, I see the problem. My picture is just very much not to scale. Let me try to make it a little bit more to scale. Just give me a second. There we go. It's a little bit more to scale now. I was confusing myself. Okay, so we know what R prime of t is, and we know that f. This is R2, by the way, for C2. F of R2 of t would just be 16t squared, comma 2 plus t squared. So the integral over c of f c2 f dot dr will be the integral from 0 to 1. The integral from 0 to 1 of, I'm going to have to go on a new page actually. Before even bothering to write all this out, I'm just going to go to a new page. So continuing along, what we're getting here is the integral over C2 of f, of f dot dr would be the integral from 0 to 1 of 16t squared I plus 2 plus t squared j dotted with 4i plus j dt, which in other words integral from 0 to 1, 32 t squared plus 2 plus t squared dt. And I'm not going to bother going through the whole integration here because this is just a basic polynomial integration. Very simple. This comes out to 83 thirds after going through that whole process. So now, with that in mind, what we can see here is that the if we're now going to actually I'll do it this way. So the upshot of all of this, we're trying to find the integral, just to remind everyone, of f dot dr, and that is going to be the integral over c1 of f dot dr, which we did earlier on, plus the integral over c2 of f dot dr, which we just did. And that's going to come out to, now the integral over c1 we said was 0. The integral over c2 we just calculated was 83 thirds. So the final answer, having done all of this, is 83 thirds. All right, so that's basically it. So if you've got some weird looking curve like this, it's very simple. All you have to do is just take care of each piece individually, and that basically solves the problem. You don't really need to worry about that. You can just do the integral of each piece individually, and that'll be fine. Now, by the way, just to think back a little bit more, and going back to this original problem, we were looking at the formulas. One of the formulas we had was this fundamental theorem of line integrals. Can we use that in this case? So could we have used the fundamental theorem of line integrals, which was that the integral over c of f dot dr is the integral over c of the gradient of f dot dr, which is f of the, which is, let me just write it even a little more succinctly, f at the end minus f at the beginning. Well, let's find out. So if we do indeed have that f is the gradient of some field, then we remember our test for this, the derivative of p with respect to y should be the derivative of q with respect to x. Is that the case here? Well, the derivative of x squared with respect to y is 0. In fact, it's always 0. And the derivative with respect to x of q, or y squared, is also 0. So it stands to reason that, yeah, actually this would work. So you can actually instead take f of the, f is going to be the antiderivative of x squared dx, which in this case is 1/3 x cubed plus some arbitrary function of y. I don't know what that function is. But taking it a step further, we know that fy in that case would have to be g prime of y, which we now know to be y squared. So anti-differentiating this gives us that g of y is 1/3 y cubed, possibly plus some constant, which we usually ignore. So yes, so fxy would work if we take this to be 1/3 x squared plus 1/3 x cubed, not x squared, plus 1/3 y cubed. So actually, this whole thing could be made much simpler if we just take the integral over c of x squared dx plus y squared dy. This whole thing is going to come out to f of the starting point we see is, or the ending point is 4, 3 minus f of 2, 0. 4 cubed is 16 times 4 is 64, so that's 64 thirds plus 27 thirds minus 8 thirds, minus 8 thirds. And in fact, the whole thing is going to come out to, going to come out to 83 thirds. Exactly what we had before, which was so much easier. The fundamental theorem of line integrals made this so much of an easier problem. It doesn't matter that we had that cusp in there. We can do it this way too. So there are two different ways of approaching this problem. So you want to write down all of the formulas you might possibly use. Let's try that. Let's apply that principle in this case. Again, we're dealing with what's very clearly a vector field integral. So there are two possibilities. We can either use the integral over C of f dot d r is the integral from a to b of f of r of t dotted with r prime of t, or we can use the integral over C of f dot dr is little f at the end minus little f at the start. Let's see if that works out. Well, we would like to use the second one. We would like to use the second formula here. So the question that we need to ask is our vector field conservative? Well, let's find out. We don't have a test for this in 3 dimensions, for three-dimensional vector fields, but we can still see if we can still try to find an anti-gradient. That's still allowed. There's nothing stopping us from trying. We'd have to have that fxyz would be equal to the integral over, would the antiderivative of x dx, which is 1/2 x squared plus some arbitrary function of y and z, which says that fy would be gy yz, which is just y. So in fact, gyz would be 1/2 y squared plus some function h of z. So now we can say that fxyz is 1/2 x squared plus 1/2 y squared plus some function of z, and fz is h prime of z, which comes out to xy. And that's a contradiction, which says that this thing is not, in fact, conservative. So the answer to this question is no. So we need to use the first formula. Fortunately, in this case, that's not very difficult because most of the important stuff has already been given to us. We know that r of t is cosine t sine t t. So that tells us that r prime of t is negative sine of t cosine of t and 1. And f of r, f of r of t. F of r of t is cosine ti plus sine t j plus cosine t sine t k. Now I'm going to run out of space, so give me a second. Okay, so since we know it's not conservative, we need to use the fact that r prime of t is negative cosine t. I did it again. Negative sine of t cosine t1, and f of r of t is cosine t sine of t sine t cosine t. So f dot dr becomes the integral from 0 to pi of the dot product of these things, which is negative sine t cosine t plus sine t cosine t plus sine t cosine t dt, which is the integral from 0 to pi of sine t cosine t dt, which, spoiler alert, is 1/2 sine squared t evaluated from 0 to pi, and that's 0. So that's the solution to the problem. So we tried seeing if it was conservative, and we immediately found that it wasn't. So that's okay. There's nothing wrong with that. It just means that we need to use a different plan of attack. In this case, this was the only really viable option for us. Let's do one more of these. Now, on the other hand, let's look at this example. So here we've got a two-dimensional vector field, which is a little bit easier to tell if it's conservative or not. And C is the curve parameterized by r of t equals sine squared of pi over 2t and t to the t for for t going from 1 to 2. Now, again, there are two formulas we can use. And the two formulas in this case are f dot dr is the integral from a to b of f of r of t dotted with r prime of t dt. Or we could use the integral over c of the gradient of little f, if such a gradient exists, which is little f of the end minus little f at the start. Now, here's the thing. This is a rather, if we try doing the brute force strategy in this case, the first one, we'd run into a really big problem. This t to the t thing is a real pain in the neck to differentiate. It's possible, but it's really crappy. So let's see if we can do this in a way that avoids that entirely. And what we hope, so the question we should ask is f conservative? Well, the partial derivative of p with respect to y is the partial derivative with respect to y of the function 2xy plus y squared, which is 2x plus 2y. And meanwhile, the partial derivative of q with respect to x is the partial derivative with respect to x of the function x squared plus 2xy plus 2e to the y, which sure enough is 2x plus 2y. So yes, it is. We can now say that fxy is going to be the integral from, or not the integral, the antiderivative of 2xy plus y squared dx, which is x squared y plus xy squared plus some arbitrary function of y. I don't know what that is yet, but I do know that fy would then have to be x squared plus 2xy, so far so good, plus g prime of y, which we know to be x squared plus 2xy plus 2e to the y. So g prime of y is 2e to the y, or g of y is 2e to the y. So that tells us immediately, tells us that f of xy is equal to x squared y plus xy squared plus 2e to the y. And that's a big help to us. Now, what's the start? The start, even though the derivative of that thing is a pain, actually finding the start and endpoints is easy. R1 is going to be sine squared of pi over 2, 1 to the 1, which is just 1, 1. And r of 2 is sine squared of pi 2 squared, which is 0, 4. Let's see if I can do this in the space I have left. The integral over c of f, I'm not going to be able to do this in the space I have left. 1 second. So we know that, so we found, rather, that f is the gradient of the function little f, where little f xy is given by x squared y plus xy squared plus 2e to the y. The start is r of 1. R of 1 is the 0.11. The end is r of 2, which is the 0.04. So the upshot of all of this is that the integral over c of f dot dr, f dot dr is going to be little f of 0.4 minus little f 1.1. And what's that? That is going to be, so little f of 0.4 is just 2e to the 4th, because x is 0, minus f of 1.1 is minus 1 plus 1, sorry, 1 minus 1 minus 2e, or in other words, 2e to the 4th minus 2e minus 2. And that's our final answer. Now that would be basically impossible if we didn't have the fundamental theorem of line integrals. It would be, okay, it would be doable in principle, but really friggin' hard. So the fundamental theorem of line integrals makes this problem so much simpler. So it's a good thing to have in your back pocket. All right, thank you everyone for tuning in or for watching the recording later on. Hope this was helpful. And we will continue our exploration into more exciting kinds of integrals next week. Bye, everyone.